Hi, my name is Scott Simpson, and today we'll be talking about balancing complex redox reactions. So there are certain redox reactions that are more complicated than ones that we've talked about in terms of general chemistry, where you have to consider if they're operating under acidic or basic conditions. And previously, we've only looked at half reactions that only have one chemical species being oxidized or reduced. We might see other ones associated. So let's talk about the different rules associated with it. So the first thing that you'll want to do is you'll want to be sure to determine the oxidation states of every atom in the system. So determine oxidation states. So as you're determining these oxidation states, this will help you figure out what's being oxidized, what's being reduced, and then you can break it down into half reactions. So let's look at an example. Let's say we have MnO4 minus reacting with, we're going to go with oxalate 2 minus, and it's going to react, and we're going to form manganese 2 plus carbon dioxide. And I'm leaving physical states off here. Okay, so let's determine what is the charge on each system. So again, oxygen's a -2. Since we have 2 of these, the carbon's going to be a +4. The oxidation state of that manganese is contained there. Oxygen's a -2. Overall, let me just turn this up a little bit. Ooh, other way. A little bit better. The carbon, in this case, we need a -2 charge overall. So in this case, this guy's going to be a +3. Then we have -2, doing that all out, +7. Okay. Next, what we have to consider is determining the half reactions. So let's try and figure out the half reactions. 2. Divide equation into half reactions. So we're trying to get those half reactions out. In this case, we're going to be looking at the manganese and the oxalate going to carbon dioxide. We're focusing on those ones because you kind of want to ignore oxygen for the most part when determining this. So the first one we'll look at is MnO4 going to Mn2 plus, and then we have our oxalate anion going to carbon dioxide. Okay, in this case, we want to determine which one's oxidation, which one's reduction. Remember, Leo goes Gur, losing electrons, oxidation, gaining electrons, reduction. In this case, we're going from the manganese from a +7 to a +2. That system had to gain electrons, so this will be a reduction. Whereas in the bottom case, the carbon is going from a +3 state to a +4 state. This is an oxidation. Okay, what we want to do next is we want to balance the half reactions. The way that we want to do this is you want to follow a set of steps. You first want to balance everything that's not hydrogen and oxygen. All atoms / elements except hydrogen and oxygen. Then you're going to balance the oxygens by adding water, H2O. Then you're going to balance your hydrogens by adding H plus. And then you're finally going to balance charge by adding electrons. Okay, so let's see how this is done in practice. We're going to focus on this half reaction right here first, and then we will move to the other half reaction. Let's get this erasing out of the way first. It's an interesting board. You can see like the ghost of what you've written on here, sort of like a can of chalkboard. There we go. Hopefully that looks clear enough. Okay. So we have our MnO4 minus going to Mn2 plus. We have to follow the situation here. We want to balance all atoms other than oxygen and hydrogen. We only have one manganese, so we fulfilled criteria A. Now we have to move on to B. We got to balance the oxygens by adding water. In this case, we have 4 oxygens on a reactant side, so we have to introduce 4 waters on the product side. So now we've balanced our oxygens, but now we don't have balanced hydrogens, so we have to do C. We got to balance the hydrogens by adding H plus. Currently, we have none on the reactant side. We have a total of 8 on the product side, so we got to introduce 8 H pluses. Okay. With that, we have the hydrogens balanced. We've completed C. Now we got to balance the charge by adding electrons. The other thing we want to keep in mind is the oxidation states of everything here. So we're going from a +7 to a +2. We're going to have to add electrons to the system because the manganese is being reduced. In order to make sure that that reduction happens, we got to add electrons to this side. The other thing is if you look at the total charge along here, we have +8 minus 1, it's a +7. On this side, we have a +2. So we got to introduce electrons to make sure that charge is conserved. So in order to do that, we have to add 5 electrons to this side. Our charge is conserved. Overall, we get a +2 on this side. Overall, we get a +2 on this side. Great, so we have our first half reaction. Let's look at our other half reaction. So in this case, we have oxalate, changing colors on this, seeing if that makes a difference. Going to carbon dioxide. Okay, let's follow our procedure over here again. In that case, we have to balance the elements other than oxygen and hydrogen. We look, we have 2 carbons on our reactant side, we need 2 carbons on our product side. So we toss a 2 there. Next, we have to make sure our oxygens are balanced. We have 4 on this side, 4 on this side, we're good to go. C, balance our H's. We have no H's to worry about, so we can exclude that. Finally, we got to balance our charge by adding E. Our electrons, overall, the charge is -2 here. The other thing is each carbon is going from a +3 to a +4 state, meaning it has to lose electrons. Each carbon is losing a total of 1 electron. Since there are 2 of them, we need 2 electrons on this side. Great. So now we have our half reactions balanced, but our overall reaction is not balanced. So what we have to do next is step 3. We need to make sure that our electrons are balanced. So we're going to multiply by a common factor to balance our electrons. Multiply by common factor to make sure our electrons are balanced. So we have 2 and we have 5 here. So what we're going to have to do is find a common factor between 2 and 5. Common factor in that case is 10. So we need 10 electrons for here. We're going to take this guy and multiply it by 2. And then for this one, we need to get a total of 10 electrons. We're going to multiply by 5. Okay, how is that going to transform this thing? This thing is going to transform after it gets multiplied through. Our top half reaction, as we multiply by 2, we get 16H plus 2 MnO4 plus 10 electrons gets us to 2 manganese 2 plus and 8 hydrogen. Then when we multiply by 5 here, we get 5 oxalating ions, total of 10 carbon dioxide molecules, and a total of 10 electrons. The next thing we want to do, we want to add these balanced half reactions together. Step 4, add balanced half reactions together. When we add those two things together, what should end up happening? Those electrons should cancel out because they appear on both the left and right. If you have anything else that matches on the left and right, those should also cancel. In our case, as we add everything together, we get 16H plus 2 MnO4 minus plus 5 oxalating ions, 2 manganese 2 plus, 8 waters, and finally 10 carbon dioxides. So this is balanced. Now, the final thing that we need to do is make sure, well, not the close to final thing we need to do, is we need to make sure that we follow the law of conservation of mass. So see conservation of mass and conservation of charge. We want to make sure the total charge on the product side matches that of the reactants, and we want to make sure we have the correct number of atoms. So check charge and mass balance. As long as those two things match, should be good to go. They do when you total everything up, at least for this reaction. Okay. The next thing that we want to do is consider if the reaction is being conducted under acidic or basic conditions. Basic conditions. Okay. If it's under acidic conditions, we need to have H plus in existence. If it's under basic conditions, what you do is you add hydroxides to cancel out these H pluses. So add balance H plus. Okay, so the reaction we have down here, this is actually under acidic conditions. We wanted to consider it under basic conditions. What we would need to do is add hydroxide to cancel out this H plus. So in order to do that, we would need a total of 16 hydroxides. Oops, I should have put 16 there, I'm sorry. Add it to the left, or excuse me, if we add it to the right, we have to add it to the left. Okay, now what is going to happen here? The hydroxide and the H plus are going to meet up and they're going to form waters. So now we have 16 waters. Okay, looking at that, if it appears on both the left and the right, we have to cancel it out or we can cancel it out. In this case, we have 8 waters here. Those are going to go away. And then we're going to cancel out those 8 waters. Therefore, under basic conditions, a reaction would have the following. 8 waters, 2 MnO4s, 5 oxalates. Oops, reaction here. Sorry, these things are squeaking like crazy. 2 Mn2 plus. I'm going to need more space, so we'll erase this guy. Followed by, I erased our carbon dioxides, 10 carbon dioxides, plus our 16 OHs. So this would be the basic conditions. So depending on what type of conditions you're doing this under, acidic or basic conditions, you can see that you will get different balanced formulas in the end, or balanced reactions in the end. So what we talked about is how to balance complicated redox reactions and to consider if it's under acidic or basic conditions. With that, I would like to thank you for watching, and if you have any questions or comments, please leave them below. Thank you.